All right, hi everybody. Welcome back to 10600. So today we're going to talk about modeling. In particular, how to start to come up with a model for a single random variable, which sounds like it might not be that complicated a question, but in fact it turns out that there is a lot to know. So let's get started. So looking at these lecture notes here, I wanted to point out a few things. So first of all, we're going to be using, throughout the mini, we're going to be using a bunch of information that we went over in the previous mini. So I've put links to that information here in the oops. I put links to the information in the lecture notes, and so I'll try to do that whenever we use something extensively that we used in the previous mini. Always feel free to ask questions about that material, and please also, if it's not familiar to you, there's lecture notes available from the previous mini, so go ahead and have a look at those. All right, so when we are making a model, I guess the first question is, why are we making a model, right? So we're making a model because we want to learn something about the world, and so our model is our description of how we think the world might act. And usually we can't make a complete description. We're going to leave some free parameters that we need to estimate. And we looked at one way to estimate those parameters last time around, which is maximum likelihood. And we'll actually get back to maximum likelihood later in this lecture. So a model as a whole is basically a list of all of the random variables that we might be interested in, the ones we observe and other ones that might affect the ones that we observe, and a description of how they are related. And so the first step, of course, is to describe the individual random variables, and that's where we're going to start today. And then on Monday's lecture, hopefully we'll get to talking about how they're related to one another. So when we describe a model for a single random variable, it's going to have some free parameters. These free parameters specify the things we don't know about the world. And so let's get started taking a look at some different ways to describe these distributions, right? So we'll go through three examples of increasing complexity. Categorical, multinomial, and Poisson. These are three models of a discrete random variable. And then we'll talk about a maximum entropy model, and we'll spend a bit more time on that because it's a very flexible and correspondingly more complicated way of making a model. So let's start with a categorical distribution. This is probably familiar already. If you have just one of k possible outcomes for an experiment, you can separately have a probability for each one of those outcomes. And the only constraint is those probabilities have to be non-negative and sum to 1. And that situation is simple enough that maybe it doesn't even deserve a separate name, but we have one. It's called a categorical distribution. And so one of the distributions that you saw was for a biased coin flip, where you could have probability of heads be 70% and tails be 30%. With only two outcomes, it's called a Bernoulli distribution. That's a special case of a categorical. More generally, you could talk about a distribution over any set of discrete outcomes. So words of the English language, states in the United States, students in a class, right? And so you could have a lot of different possible categorical distributions, and the more outcomes you have, the more parameters there are. And sometimes there might be actually a rather unmanageable number of parameters, and so we'll talk later about how to try to deal with that. All right, so that's categorical. The next one I wanted to mention is multinomial. So A multinomial is basically a repeated categorical variable. So what that means is, let's say we take n samples from a distribution, a categorical distribution. So n coin flips or n draws of a state from the United States, or n draws of a student from our class. And we count the number of outcomes, right? So for the states, we could count how often each state came up, or we could count some derived outcome like how many letters there are in the name of the state, or what's the population of the state. And so when we do this, we get a vector of counts. The counts are all non-negative, and they sum up to n, the total number of experiments. So our coin example, we could have 17 heads and 3 tails, or 10 heads and 10 tails, or any other number. And again, there's a special name for the case of only 2 outcomes. It's called a binomial distribution. So a Bernoulli turns into a binomial, a categorical turns into a multinomial. And you've probably seen people plot samples from a multinomial random variable before. Anytime you see a histogram, that's representing a sample from a multinomial random variable. It's dividing the world into bins and telling you how often each bin came up. And so there's a nice example of a histogram here where I randomly selected a state from the list of 50 in the United States, and did that uniformly with replacement, and counted the number of characters in the name of the state that I got. And so 8 characters turns out to be the most frequent length of a state name, and you can see that 8 characters is in fact the most frequent outcome in our sample. As a matter of fact, if you go down here, 24% of states have an 8-character name. And we actually had extraordinarily close to that, 29 out of 123. So 0.2358 was the actual fraction in our sample. That, by the way, is closer than you would expect to get by chance, but we got lucky on this particular example. And one of the things, so with a categorical distribution, the model is very simple, right? It's just probability pi of outcome I. Here, if we have a multinomial, the expression is slightly more complicated. If we have x1 copies of outcome 1, x2 copies of outcome 2, and so forth up to xk copies of outcome k, the probability of seeing that is the product of pi to the xi, right? That tells you how probable it was to get I copies of outcome I. But then there's this correction term that involves a bunch of factorials that tells you, it basically corrects for the fact that we are ignoring the order in which we get the outcomes. We could get all of the outcome 1s first, or we could get 1, 2, 1, 3, 2, 1, right? And those lead to the same sample because we're just counting the total number of occurrences. All right. And so, lest you think that the world is all categorical, the Poisson distribution is another useful model of a discrete random variable. So just like a multinomial, it is a count, but it's a count in a very different situation. So what we're thinking of is there's an event that could happen at any time. Like, for example, a car could drive by an intersection, or a customer could arrive at a restaurant. And we're going to observe for some fixed period of time. Let's say we sit at the intersection of Forbes and Morewood for 20 minutes and count cars. Or, we could count, let's say, blue Toyotas, or, something like that. And there's some rate at which blue Toyotas pass through that intersection. And so the resulting distribution of the count that we get is a Poisson distribution, and it has one parameter, which is the underlying rate, the underlying number, the average number of blue Toyotas we'd expect to go by our intersection in 20 minutes. And here is the expression for Poisson distribution. So x is going to be an integer. It'll be just one count. And the probability of getting x counts is lambda to the x, e to the minus lambda over x factorial. And so a plot of that is something like this. This is one where the expected number of counts is 7. And you can see that having either very few or very many counts is unlikely. Right. So I should say, by the way, that these expressions here, you don't have to remember them because you can look them up on Wikipedia or on in the back of a statistics textbook. You just have to remember that a Poisson distribution is for measuring a count when you have an underlying rate at which the events arrive independently. So I have a question about whether the multinomial is actually a distribution. I think maybe that's a confusion over what the sample looks like, right? So a single sample from a multinomial is a vector of counts, right? So it's if there are two outcomes, like for a coin, it would be a pair of counts, like 17 and 3. So it's a distribution over tuples of integers, right? And so it's much more complicated, right? The categorical was just a distribution over a number from 1 to k, right? Which outcome happened. For a multinomial, we have k separate numbers, one for the count of each one of them. And it is in fact a distribution. There's a probability of getting each different vector of counts, and the sum over all possible vectors of counts is 1, right? And if you want the probability of any specific vector of counts, it looks like this. All right? So let's see. So I've given 3 examples of discrete distributions, and they all look pretty different, right? The Bernoulli or categorical, that's a distribution over just one of k outcomes. The Poisson, that's a distribution over a single integer, which is the count of our event. And the multinomial, it's a distribution over a whole vector of counts. And you can write down the formula for the probability of a given sample. But they're all, these are all valid distributions. And I picked these 3 for a couple of reasons. One is that they all show up fairly often. And the other is that they're diverse. They show some very different looking samples and different looking ways to evaluate the probability of a sample. All right. Now I could go and just spend the rest of today's lecture, or actually I could probably spend the rest of this entire mini listing different distributions and explaining what they're for. And I'm not going to do that, so don't worry. Instead, what I'd like to do is use these as an example and go up a level of generality. I'd like to talk about how to construct a model for a discrete random variable, right? And that discrete random variable, it could be an integer, one of k outcomes. It could be a distribution over strings, like words in the English language. It could be a distribution over tuples of integers. As long as it's discrete, what we're going to talk about will work, and it'll be a very general recipe for making a model of a single discrete variable. All right. So, how are we going to do this? We're going to do it based on features. So for every discrete outcome, we're going to assign a vector of numeric features. So if our outcomes are integers, it's easy to think of features, right? Like you could have x and x squared and 1 over x, right? Like various different numeric functions of the integer. If our outcomes are strings, you could have something like the length of the string, or you could have something like how many vowels are in the string, right? Or what's the largest number of consecutive consonants in the string, right? Like for every discrete data type, you can probably think of a whole bunch of features that you could evaluate, where a feature is just some function where you put in an element of your data type and it comes out with a number, right? And so this description in terms of features, it's both a blessing and a curse, right? It's a blessing because it's very flexible. You can do it with just about any data type that you can think of, right? Binary trees, hash tables, right? You know, any discrete data structure you can think of. It's a curse because there's so much flexibility, right? So for any given problem, you're going to have to think hard to come up with what are the features that are relevant to measure for each one of your outcomes. And we'll come up with some examples of that in a little bit, but for now let's assume that the outcomes are integers and that we're measuring features like x or x squared. All right, so features make a good way to describe a probability distribution because I can ask what is the expected value of a feature, right? So for example, suppose I have my features as x and x squared, and I'm going to have a distribution over the integers 1 to 10, right? So I've got two different distributions here, right? There's this distribution here where the probability of x is just x over 55, right? So that means that like the probability of seeing 1 is 1 in 55, the probability of seeing 10 is 10 in 55, right? So this is a distribution where larger numbers are more likely. This distribution is just the uniform distribution over these 10 outcomes, right? Each of the 10 outcomes has an equal 10% probability of happening. So if you calculate the expected value, you just write a short MATLAB script or whatever. The first one has expected value 7, and the second one has expected value 5.5, right? And so that's the expectation of the first feature. The second feature is x squared, and the expectation of that feature in this distribution is 55, and in this distribution it's 38.5. Right? And so these two different distributions differ in the expectations of these two features. Right? And so we can think about using the features to characterize the different distributions and saying that I would like to describe whatever my distribution is by listing what the expected value is of each one of these features. So if we go back to the example of states, for example, I could say, what's the expected number of letters in the name? Or if I go back to the example of words in the English language, I could say, what's the expected number of vowels in a word in the English language, right? Or the expected squared number of vowels, or the expected max consecutive number of vowels. And I can come up with almost an infinite number of features like that. And obviously I want to pick, you know, a finite subset of that infinite variety. So the expected value of a feature is important enough that it has its own name. It's called a moment of the distribution. And if the features are low order monomials like x, x squared, x cubed, there's an even more special name, right? The expected value of x is called the first moment, of x squared is called the second moment, x cubed the third moment, and so forth. All right, so just to have some notation, I'm going to write t of x for the vector of features. So t of x could be x and x squared. I'm going to write t bar for the vector of moments, meaning the expected value of x and the expected value of x squared if we sample x from our distribution. All right, so features are a good way to describe distributions. Now, what I'd like to do is to use a vector of features to help us build a model, right? And so if we choose a good and relevant set of features, hopefully we get a good and relevant model of our discrete random variable, right? Meaning we get a good and relevant set of distributions to use. Hopefully one of them is close to what we actually observe in the real world. And hopefully we can fit the parameters of this model. So how do we choose these features besides just being relevant and cool sounding? One way to think about it is to say that if we choose some function as a feature, we're saying we don't know the corresponding moment ahead of time. Right? So if we choose x, that means we don't know the mean. If we choose x squared, that means we don't know the variance, right? And so if you think about the process of building the model, you'll start by saying, okay, what is something I don't know about the distribution, right? Maybe it's mean. And so I'll add the corresponding feature to my set of features. And then I think, okay, given the mean, what do I still not know? And the variance might be a good example, and so I'll add x squared to my list of features. And then you might have something like, well, I mean, it'll depend on what the what the application is, but hopefully you'll be able to keep adding features based on your idea of what could change independently about this distribution. Right? And so maybe a source of confusion is that these features, I mean, they can be used two ways, right? They're used to describe an individual sample from the distribution that will have some value for each of the features, but they're also being used to describe the distribution as a whole, meaning that you're describing the distribution by saying what's the expected value of the features. All right, so given this vector of features, we'd like to use it to build a model, right? And so one attractive idea would be to say that the vector of moments is a parameter of our model, right? So we fix a set of outcomes that we're going to be looking at, like, let's say, the non-negative integers, and we fix a list of features ahead of time, let's say x and x squared. And then when we want to pick a distribution over these outcomes, we specify it just by specifying what's the expected value of x and what's the expected value of x squared. And this is a good idea. It's a good enough idea that it has a name. That's called the mean parameterization of a family of distributions, because we're picking our parameter to be a mean of the feature vector. Now, the problem is there could be lots of probability distributions that have the same mean, the same vector of moments. And so if we're going to do this, we have to decide on a rule for which one to pick. So given that we did information theory on Monday's class, one good idea might be to pick the distribution that has the highest possible entropy given the set of moments that we've picked. Equivalently, right, so why would we pick that one? We would pick it because high entropy means low information. So we're assuming as little as possible about the distribution, assuming as few bits of information as possible about the distribution beyond what we know given the moments, right? And so that's an attractive sounding rule, and it's called the maximum entropy or maxent distribution. And we can parameterize it using our vector of moments. Now what we're actually going to do is slightly more complicated, not much. We're going to, instead of maximizing entropy, we're going to minimize the relative entropy. So if you remember, the relative entropy is, suppose that somebody knows a distribution P0, how much more information do you have to tell them than if they knew that to describe a sample from our distribution than if they knew the true distribution P, right? And so P0 is arbitrary. It's called the base distribution, but you can pick it in different applications. You can pick a base distribution that makes sense for that application. So these two things, maximum entropy and minimum relative entropy, are ways to specify which distribution we mean when we give a vector of moments. All right, so that is all very well and good, but that's an implicit definition of the distribution. Can we get an explicit form for what is the distribution that maximizes the entropy? And the answer is yes, although sometimes it's still kind of difficult to compute. So this form right here, right? This form is called an exponential family of distributions, and it is interesting, it is important, because you can always write the solution to the maxent or to the minimum relative entropy problem as a distribution of this form. So what does this form look like? Well, it's got an exponential function in it. That's why it's called an exponential family. It's got P0, that's our base distribution, right? So our base distribution, think of it as uniform to, if you want to make things simple, but you could also say, for example, that our base distribution could favor small integers, or it could favor states close to Pennsylvania, or something like that. We have our moments, right? So this is our feature function. So remember, t of x is our vector of features for a particular point x. And we're going to have a parameter theta. And so it's going to be e to the t dot theta, right? So the probability of x is going to be proportional to e to the t of x dot theta. So meaning that if you take a particular component of theta and make it big, that's going to favor points that are, it's going to heavily favor points that have large values for the corresponding feature, right? So theta you can think of as which features do I prefer or disprefer, right? So I can disprefer them by making theta very negative as opposed to very positive. And then we always have to sum to 1, so we're going to put in an arbitrary, well, not arbitrary, we're going to put in a normalizing constant, and that normalizing constant is completely determined by the requirement that the distribution has to sum to 1. All right, so this is maybe an arbitrary seeming form, right? And you'll have to trust me that it is in fact, that you can always write the solution to the max-ent or to the minimum relative entropy problem in that form. It's a fun exercise to derive it, but maybe outside the scope of this course. But given this form, we can start looking at what does it imply? What are its properties, right? So the first question is, how do we compute G, right? And so the naive answer to that is, well, we just compute G by picking a particular value of theta and then summing this expression over all possible values of x, right? And then you set g of theta to be the log of the sum, so that when you multiply by e to the minus g of theta, you normalize to sum to 1. Now, that is not always computationally feasible, right? So if your distribution is over heads and tails, then it's really easy to sum over 2 outcomes. If your distribution is over words of the English language, well, there's maybe 50 or 100,000 words in your dictionary. It doesn't take that long to sum over that. If your distribution is over integers, well, you might have a little bit more of a problem. For I equals 1 to infinity is probably a bad thing. But, maybe there's, you can approximate it pretty well by summing over up to 1,000,000, right? Or up to some, largest reasonable integer. But when you start to get to, there are, the number of depth 10 binary trees that are labeled at their leaves with English words, right? That's a ridiculous number of things, right? And so there's no way we're ever going to be able to sum over that. And in that case, we actually have a great deal of trouble computing this function g. And one of the things that you'll learn about if you go on into machine learning courses is strategies for approximating that sum so that we can work with this family of distributions. All right, so that's the normalizing constant. The second thing is the parameter vector theta, right? Like, so I said above that I wanted to use the vector of moments, the mean parameterization of our distribution. And here my parameter is theta instead of t bar. And so we find theta by solving this equation. The gradient of g at theta should be equal to t bar. That equation should seem arbitrary to you because the derivation is in no way obvious, but I'm actually going to derive it in a few minutes. But let's just type check, right? So g is a scalar function whose argument is a vector theta. So g prime, the output of g prime, is a vector of the same size as theta, right? And theta is the same size as t because we have one parameter per feature. And so, you can at least type match this, right? This is a vector of k real numbers, and this is another vector of k real numbers. There's also, this is, again, we're not going to prove it, but the function g is always differentiable, so g prime always exists, and it's always invertible, meaning that if there is any probability distribution at all over our outcomes that has the desired set of moments, then there will be some theta that achieves that set of moments. Although if it's on the boundary of what's achievable, you might have to take an infinite or arbitrarily large theta in order to achieve it. All right, so this is a very, very general way to specify a distribution, so let's step back for a second. And say again why we care, right? So we care because we would like, it's nice to have a general way to specify a distribution over a discrete set of outcomes. And this is actually, despite it being a complicated expression, it's actually a fairly user-friendly way to specify a distribution, because you pick it by picking what are the features that you're going to use to represent the distribution, right? And we have a lot of intuition about how to select features for a given problem, like what features might be relevant to thinking about a given problem. All right, so so please ask questions if all of this isn't clear. I'm going to do two things next. One of them is I'm going to go through this derivation. So this derivation is just showing that this equation here is correct, that if we select g prime of theta to be t bar, then we will actually have the desired vector of moments. The other thing is I'm going to keep on with the lecture notes and talk about what are some examples of exponential families of distributions. Actually, maybe let's do the examples first. You can always come back and do the derivation. All right, so the Bernoulli distribution is actually already an example, right? So here are outcomes, right? So we have outcomes of 0 and 1, right? So this is for a Bernoulli. Our base measure is uniform, so we have P0 is equal to a half or a half for 0 or 1. And so what that means is our probability, right, our probability distribution, P of x, where x is either 0 or 1, is equal to e to the t of x dot theta, right? So we have to decide what our features are. And I'm just going to pick the single feature of x, right? So it's just going to be e to the x theta minus the normalizing constant, right? So that's equal to e to the minus g of theta if x is equal to 0, and that's equal to e to the theta minus g of theta if x is equal to 1, right? And so the sum over all possible values of x of p of x, that's equal to p of 0 plus p of 1, which is equal to I'm going to factor out the e to the minus g of theta, and so I'll have 1 plus e to the theta times e to the minus g of theta, right? And so this is supposed to be equal to 1 in order for it to be a probability distribution. And so that says that g of theta, if we just solve that, that's log of 1 plus e to the theta, right? And so that means that p of x is equal to e to the minus g of theta, right? So that's 1 over 1 plus e to the theta if x is 0. And it will be e to the theta over 1 plus e to the theta, right? So this is supposed to be a brace if x is equal to 1. All right? And if we plot that, I guess it's easier just to plot, like we'll plot just this one. Right, so as theta, right, so this is the theta axis. If theta is very negative, e to the theta will be very small, and so this will be essentially 1, right? If theta is very large, e to the theta will be very large, and this will be essentially 0. If theta is 0, this will be e to the 0 is 1, and so this will be a half. So we know it'll go through a half like that, right? And so we'll get something that looks vaguely like that, right? And so we'll be able to get every probability between 0 and 1 by taking theta to be, you know, something between plus and minus infinity. And so I've got a question, is theta something that we can derive? Yes, right? So we know, if we go back up in the notes, we can derive theta by solving this equation, right? So in particular, right, this implies that g prime of theta is equal to 1 over 1 plus e e to the minus theta times, sorry, e to the, not minus, but plus theta, right? 1 over, the derivative of log is 1 over x times the derivative of what's inside, which is e to the theta, right? Which is then, I'm going to bring this, multiply the numerator and the denominator by e to the minus theta. So I will get e to the theta times e to the minus theta is 1 over e to the minus theta plus 1, right? So 1 over 1 plus e to the minus theta, right? And so that is, that tells us the expected value, right? So we want, the expected value of x is just the probability, right? So the probability of 1 is equal to, sorry, it's not equal to that. Right, so this is equal to the expected value of our Bernoulli distribution, which is just the probability of getting 1. And so we can solve this equation to get any desired probability of 1. We figure out what is the corresponding value of theta. All right. So that's an example of an exponential family of distributions, right? It's a simple example. It's got just one parameter, either theta or the probability, and you can go back and forth between those two ways of parameterizing it. And so, you know, in this example, it seems kind of silly to go to all of this extra trouble to model it that way. And in fact, it is kind of silly for it just to Bernoulli. But it's nice to see an example that we've already seen before expressed in the form of a exponential family. Maybe another interesting example is the Poisson family of distributions. It turns out that if we take a distribution over the non-negative integers, if we take our base distribution to be proportional to 1 over x factorial, right? So in the base distribution, small integers are much more likely than large integers. And if we take our feature vector to be, again, just the single feature x, so it's only the mean that of the distribution that we're varying, then we get the Poisson family. And let's maybe it's worth doing that in a little bit more detail. So if we go back up, right, here is in the Poisson, we have p of x is equal to lambda to the x, e to the minus lambda, call that p sub lambda of x, over x factorial, right? And so we can write that, if we go back, if we go back now to the definition of an exponential family, right? So here's the form for an exponential family. If we take p0 of x is proportional to 1 over x factorial, right? And if we take our feature vector, t of x is just equal to x. And if we take our theta, I'm just going to write the right answer. So theta is going to be the natural log of lambda. Then p sub theta of x, just copying this, it's going to be p0 of x, 1 over x factorial, exp of t of x dot lambda, so that will be x times log, t of x times theta, which is x times log lambda, minus g of theta, which is the same as g of lambda because theta is a function of lambda, right? And so this is equal to 1 over x factorial. E to the x log lambda is the same as lambda to the x, right? And then e to the minus g of lambda, well, there's only one term left here, so it's got to be e to the minus lambda. Right, so that means that we've just determined g of lambda is equal to lambda. And so now I've used these definitions here to express the Poisson distribution as an example of an exponential family. So I have a question about what the meaning of the parameter vector theta is. That's a really good question. So let's see. So the first meaning of theta is that it's the function that when you it's the vector that when you apply g prime to it, you get the vector of moments. That's not very satisfying, right? But it is a one-to-one function of the vector of moments, right? So it gives you the same information as the vector of moments. The other intuition for what theta means is what I said earlier, right? So you can see here that large components of theta favor large values of the corresponding feature, and very negative components of theta favor very negative values of the corresponding feature, right? Because that makes both of those make this e to the t dot theta more positive. Geometrically, I mean, there's a lot of beautiful, there's actually an entire field called information geometry, which is about trying to understand what the geometric meaning of theta is. It's not clear how much of that is useful to somebody who's practicing machine learning. It is clear that it would take an entire course to go into it, so maybe not that helpful right here. I guess maybe the best thing I can say about the geometry is that it's much easier to interpret it in specific cases. So like, for example, here, we know that theta is log lambda, so the theta is just the log of the rate, the log of the expected number of events in the Poisson distribution. All right, so if you want to try an example for yourself of expressing a distribution as an exponential family, the negative binomial is a pretty decent example. But basically, a lot of the common forms of distribution happen to be exponential families. So that's another reason why exponential families are important, is that they happen to include a lot of distributions that people work with anyway. But maybe more interesting is that we can build an example by choosing feature vectors the way I described above, right? So let's say we're entomologists and we're tracking a kind of bug that's native to the area around Pittsburgh, and we could divide that area around Pittsburgh into plots of land and look at sightings of our favorite insect. And you can think of that as a categorical distribution over plots of land, right? Whatever the next sighting of the insect is in, whenever you get the next sighting of the insect, what plot of land is it going to be in, right? And so, you could imagine dividing the greater Pittsburgh area into, 100 meter by 100 meter squares, right? And that would be a lot of plots of land. And so you wouldn't want to learn a separate probability for each one of those plots of land. And so instead, we can look for features of these plots. Things like what's their elevation, or what's their rainfall, or what's their seasonal variability in temperature, right? So you can look up all of those things from, the National Weather Service or the National Geographic Survey, right? This data is available, and you can make a feature vector for every plot of land, and then you can try and fit one of these distributions to the actual observed distribution of insect sightings and learn something about what the habitat of your insect is. All right, so stepping back up, there are the procedure here is we want to make a model of a discrete random variable. So we assign a vector of features to each possible one of our discrete outcomes. And we choose these features based on our knowledge of the problem. And then we assign our distribution by picking what the mean value of each one of these features is, what the expected value of each one of these features is. And after we've done that, the way we derive the distribution is by maximum entropy or by minimum relative entropy. They're essentially the same procedure. And the solution is always going to be of the form that I showed above, the exponential family of distributions. And so we can solve the max ent, or the minimum relative entropy problem, by finding the vector theta. And then we'll have an explicit expression for what the probability distribution of all of our random variable is. All right? So this makes a very general way of describing a probability distribution. Now, to give us a little bit more practice, I think it's still worth going through this derivation. So I'm just going to write it out again here so that I can go through each step. So what I'm trying to show is this bottom line, right? So that whatever theta is, if we take g prime of theta, that's going to give us the expected value of the feature vector, right? In other words, it's going to give us the moments. And so that means that if we want to find the right theta, we have to solve the equation g prime of theta is equal to our particular vector of moments. And the way we derive it is maybe a little surprising. We start with the equation 1 is equal to, I wrote an integral here, but it should actually be a sum, right? The sum over all possible values of x of p theta of x. I'll fix that after class. Right, so this is, we know this is true because all probability distributions sum to 1. But we know, since we know it's true, we can differentiate both sides with respect to theta. So 1 is a constant, so its derivative is 0. Sum over x, the derivative passes through the sum. We get d by d theta, p theta of x. Right, and that's sum over x. We remember, let's see, we have the expression for p theta up here, right? It's this. So d by d theta of p theta. Well, the p0 of x, so the one that I did here is actually for the maxent case, but I'll do the full minimum relative entropy case here. P0 of x, the derivative of e to the something is e to the something. T of x dot theta minus g of theta, right? And then by the chain rule, we take the derivative of this part here, right, which is derivative with respect to theta here is t of x. The derivative with respect to theta here minus g prime of theta, right? So this, sorry. So we got this line, this second line here by differentiating the first line, and this third line by just filling out the value of p theta and propagating the derivative through. All right, sum over x. So this part here, that's just p of x, p theta of x again, times t of x. And actually, what I'm going to do is I'm going to split apart this sum, right? So now I get the sum over x of p of x times g prime of theta. This doesn't depend on x. And so the sum over x of the probability is just 1. And so I'll just get g prime of theta, right? And so I get, as promised, g prime of theta is equal to the expected value of t of x, right? Because the expected value is just the sum over all x of the probability of x times the value of the thing we're taking the expected value for. Somebody's asking, is the maxent and the minimum relative entropy solution equivalent? So they're equivalent if your base distribution is uniform. If your base distribution is not uniform, then the minimum relative entropy solution will be different. So the minimum relative entropy is a generalization of maxent. All right. All right, so the next thing that I wanted to do was to talk about how to fit this sort of distribution to data, right? So I've gone and described a very general family of distributions. And I've talked about how to specify an element of that family by picking what's the expected value of our feature vector t of x. But that's not how, like, you know, I can specify it that way if I know ahead of time what the expected value is going to be. but what if I just want to fit it to some data that I observe, right? So what if I want to do maximum likelihood, right? So maximum likelihood says that I should pick my parameter vector theta, right, to maximize the probability of the observed data, right? Which is the product over my samples. Let's say I'm going to index my samples I, p theta of xi, right? Which is the same as max over theta, the sum over I of the log of p theta of xi, right? And right here is the here's the distribution. So p0 of x is going to be it's just depending on x, not theta, so it doesn't affect the maximization over theta. So I just take the log of this, right, which is t of xi dot theta minus g of theta, right? So this is how I determine theta, right? I determine theta by maximizing the likelihood, meaning the probability of my observed vector of examples, right? So I have examples x1 up to xn. And so this is the sum from I equals 1 to, product from I equals 1 to n, or the sum from I equals 1 to n. And how do I do this? Well, I can do this by differentiating and setting to 0, right? We also have to check that we're not on the boundary and that it's an actual maximum, but in fact that's going to be true. So we can do it by differentiating and setting to 0. So the derivative of this term, the theta just drops off. And so I have 0 is equal to the sum I equals 1 to n t of xi minus the sum from I equals 1 to n, but that's just, since this doesn't have an I in it, that's just n times the derivative of this term, which is g prime of theta. In other words, g prime of theta is equal to 1 over n, sum from I equals 1 to n, t of xi. And I'm going to call this quantity, just by definition, t hat. So this is kind of interesting, right? It looks really, really similar to what we did before. If we knew the mean vector, t bar, we would just take theta so that g prime of theta equals t bar. If we don't know the mean vector, what this says to do is we compute we compute the average of our sample, and we call that the mean vector, and then we solve for theta in exactly the same way, right? So that's kind of nice, right? It means that we wanted to build a family of distributions whose parameter was equivalent to telling us what the mean of our vector of features was. And if we do maximum likelihood, it turns out that the recipe for maximum likelihood just says pick our parameter so that the predicted mean, g prime of theta, is the same as the observed mean, the average of t of xi for all I. Right? So that's kind of nice. It means that we can do maximum likelihood just as easily as we can specify one of the distributions in the first place. All right, so that's the end of this set of lecture notes. What I wanted to do next was to hand out some problems, or actually just one problem, for people to work on. That exercises this stuff that we've been talking about. So I'm going to go ahead and post the problem set, the problem on Piazza, and it's going to be due This one will take a little bit longer than the ones we did on Monday, so we're going to make it due not today, but next class, Monday, at midnight that day. So I've posted it to Piazza now, and so everybody should be able to take a look at it. And what I'd like is for people to read through it now and ask me questions. Oh, and by the way, we will shortly put up the link for submitting it. So don't worry, you shouldn't be, if you can finish this right now and be ready to submit it, then that's great. Just wait until we put up the link. But we'll put up the link within the next day or so, which should be in plenty of time for people to submit. All right, so we haven't gotten a lot of questions yet about the assignment. I don't know whether that's because the assignment is perfectly clear or because people have not yet gotten to the point of being able to ask questions about it. You know, we'll continue to stick around. I'm going to go ahead and close down the lecture stream, and my office hours start now, so you can feel free to ask me questions in office hours. And if there's a common question, I'll try and post the answer on Piazza. So good luck with the exercises, and I will see you guys next class.